Okay, we're going to get started. Hello, and welcome to today's webinar, AS Interface Safety at Work, Safety Process Simplified, brought to you by AS Interface. I'm John Appleson, and I will be today's moderator. Discussing today's topic from AS Interface will be Kartik Vashi, Application Product Manager for Schmersel, and Glenn Simons, Product Manager for Siemens Industry. Kartik is an industry safety expert with over 11 years of experience in helping customers determine their machine safety requirements, and has given many safety seminars on various topics of machine safety. In the process of making workplaces into safer places, Kartik has supported projects and advised project engineers and design engineers with machine safety products during design and integration phases. Glenn Simons is a Siemens Product Manager for ASI Systems, Safety Relay Systems, and Smart Motor Management Systems. With nearly 30 years of experience in industrial controls and automation, Glenn acts as a machine safety consultant, working with machine builders and end users to provide safe machines for manufacturing industries all over the world. During the Q&A session, Kartik and Glenn will be joined by Dr. Helga Hornis, Technology Director with Pepperland Foods. You may ask questions at any time during the presentation by typing in the Q&A panel. Please enter questions as they come to mind. Our speakers will address them during the Q&A session or by email at the conclusion of the webinar. So at this time, I'd like to hand it over to Glenn.
All right, well, thank you, John, and welcome again, everyone, to our webinar. We appreciate you taking the time to be with us today. We know everyone's busy, and we hope you'll take away some valuable information by the end of the session. So let's get started with the topics that we're going to cover today. We'll start with some facts about AS Interface, or ASI as it's commonly called. We'll talk a little bit about the value of machine safety, what that really means, and how machine builders go about making a safe machine. The safety piece of ASI is known as ASI Safety at Work, or simply ASI Safe. And we'll talk about why that's a good fit in the making of safe machines and how that actually occurs. And finally, we'll share some real-world safety applications and solutions that feature ASI Safe technology. So to begin with, if you're involved with industrial automation, chances are that ASI is somewhere nearby, whether you're in factory or discrete automation, process automation, building automation, or even mobile equipment automation. ASI is a technology that fits pretty well and, in fact, has proven benefits in automation and control solutions in all of these areas. ASI is the second most utilized industrial network in the world, second only to Profibus. ASI has over 36 million ASI devices installed worldwide. There are 350 members, plus members of the association who make automation components, and we provide over 1,900 certified ASI products. And so the trend, if you look at it off into the 2025 time frame, which really isn't that far away, it's projected that there'll be over 60 million nodes, nearly double what it is today. One other item of note, ASI, when implemented with ASI Safe, is the most successful low-level safety bus in the world. There are more than 7 million ASI Safe devices in operation today, so it's a pretty substantial amount. So let's talk about the value of machine safety and what that really is. According to data from the U.S. Bureau of Labor Statistics, over 1,000 workplace fatalities occur each year in the manufacturing, mining, and resources, which is essentially oil and gas retrieval industries. That's over 1,000 people killed consistently each year, and 65% of them die due to contact with equipment or objects, so something they run into or something that runs into them. In addition, another almost 700,000 injuries occur in those industries and due to those same causes. So it's a pretty risky business of these industries. More data on this topic, according to the Occupational Safety and Health Administration, OSHA. A poll of chief financial officers from major manufacturers reveals that they value productivity and reduced cost as major drivers of workplace safety. In fact, 70% of their concern appears to be with cost and productivity. So two things about this. One, we know that ASI technology lends itself to better productivity and lower cost. And two, the added benefit, as we hope to show here today, is that the ASI Safe technology provides even further benefits in those areas. So why machine safety? Well, the main reasons why machine safety systems are implemented in the first place are for the protection of people, the machinery involved, and the environment. Those are some pretty important reasons, obviously, and protection is really the name of the game here, and that's what we're focusing on. And the way protection is achieved is through risk reduction. So when a machine builder designs a machine, they perform something called a risk assessment for that machine. That means that they identify the hazards on the machine and take measures to reduce the risks associated with each of those hazards. The output of a risk assessment is usually measured in safety levels, and depending on the machine safety standard the machine builder is using, it could be safety categories, which a lot of us have heard of, performance level or PL levels, or safety integrity levels or SIL levels. Now, we're not going to go into those topics here today, but just know that the risk assessment is how a machine builder would quantify the risks for every hazard on the machine, and from here they determine how best to mitigate each of those risks. So here we're showing a cutting machine. I hope you can see that there's a spinning blade on it. There's some clamping at the front end for the feedstock, some rollers at the exit end, and all have hazards associated with them. So in the design of the machine builder has to take measures to eliminate or reduce the risks of each of those hazards. So he has to protect, remember, the people, machine, and the environment. The first step in doing so is to design in the safety features that help to reduce or eliminate the risks and hazards. So in our example here, one design measure to help to reduce the risk of someone being hurt by the spinning blade, for example, might be to implement the stock feed system that you see here. So that would keep the personnel away from the blade. Once that's implemented, the machine builder has to continue to design in mechanical safety features until they've done all they can to reduce or eliminate the risks associated with those identified hazards. The next step the machine builder has to take is to implement technical measures. So these measures could include adding safety technology devices such as light curtains, e-stops, safety relays, and so on. And again, the machine builder has to continue to design in these technical safety features until they've done all they can to eliminate the risks associated with all the identified hazards. After the mechanical and technical safety measures have been implemented, the final element is operational or organizational measures, and that could include training for operations or maintenance personnel, signage around the machine, fencing, guarding around the machine, for example. And only after all these safety measures are implemented can the machine builder be sure that their machine is as safe as it can reasonably be and ready for operation. So for the purpose of our Aussie Safe discussion today, we'll focus on the technical measures for risk reduction on a machine. And what are we talking about with technical measures? Well, technical measures in the context of machine safety are really about automation or control solutions that include three main components that you see here. So detection, evaluation, and reaction. Detection is really the monitoring of the conditions on or around a machine, and those can be accomplished by way of sensors such as e-stops, gate switches, safety mats, light curtains, those kind of things. If you're in a plant, you see those around all the time. Some means of detecting a hazardous situation. Evaluation is really the logical assessment of what's been detected. So that could be accomplished by a fail-safe PLC, for example, a safety relay, or in the case of Aussie Safety at Work, or Aussie Safe, a device called a safety monitor. And we'll get around to that. And then reaction is the action of removing the hazardous motion or process, either by coming to a safe speed, managing a process variable like level, flow, temperature, etc., or by simply shutting down all or a portion of the motors associated with the machine. So why is Aussie Safe a great solution? Well, let's look at a traditional hardwired safety circuit first. As I said, it would consist of those three elements: detection accomplished by the e-stops and interlocks that you see here, evaluation done by the safety relay in the middle, and then the reaction accomplished by driving the contactors on the right. Typically, these are in the field wired in series, and if anything in that series is activated, we want the machine to shut down or come to a safe speed, again, whatever the reaction consists of. So this is a fairly simple safety circuit, really, and even so, you can see there are a lot of connection points, a lot of individual wires, and with that comes the potential for wiring errors. You can imagine that a complex safety circuit might consist of a lot more inputs, a lot more outputs, and potentially hundreds of wires. And remember that most, if not all of those wires would probably be run in a conduit or multi-conductor cables in a cable tray, all driving up the cost for that application. Also keep in mind that the function of the safety relay when it's hardwired like this is really dependent on the configuration of the hardwiring of the attached inputs and outputs. So system flexibility is really limited, both in terms of functionality and if you think about future expansion, you're really pretty limited if you've hardwired it. So in addition to the safety circuit wiring, to monitor those circuits, you'd also have to run additional wiring back to a PLC or some other control device, and you also have to map all the inputs into the PLC, and that creates additional labor costs, obviously. I also want to emphasize really here that the additional wiring associated with the hardwire safety circuit creates additional costs. So all that wire itself is an additional cost, but also those wires have to be run either in conduit or cable trays, so there's another cost. Each wire has to be labeled, there's an additional labor cost, and they all have to be landed, sometimes multiple times, like in marshalling panels or junction boxes, adding even more labor cost. So not to mention the opportunity for wiring errors. We're all human, we've made the errors, and that potential is really enormous, the larger the application, and that could potentially cause added complexity in the application all the way from commissioning through startup and into the maintenance phase down the road. So you can see that these are adding up. The costs are really adding up here for a traditional safety solution using hardwire. So let's look at the same type safety system using OSI-Safe. And as you may already know, if you have experience with OSI or if you attended our last webinar, you can run safe and standard signals on the same OSI cable. It doesn't matter. They all can live together on the same cable. Devices are attached to the network in whatever network configuration is convenient. The network can be a ring, star, linear, a combination of topologies. OSI really doesn't care, and it's the same in OSI-Safe. As always, an OSI master is used, of course, as shown up on the left here. It controls the communication on the network, and that OSI master can either sit in a PLC rack, like we're going to show in a second here, and or it can be a standalone device. There are a lot of devices from a lot of manufacturers out there. Safe input and output devices can attach also directly to the network, just like the standard devices. And what makes these devices safe, as it were, is an OSI-Safe chip and a special communication method that we'll go into in just a minute. Now, the safe functionality on the OSI-Safe network is really added when you put a safety monitor on the network. And the safety monitor does just what its name implies. It monitors the safe signals on the network. So it just sits and listens. So status of the input devices, as well as feedback from the contactors, is now available over the network for a control system. So in this case, we're showing a PLC, which is connected to the network via the OSI master in the PLC rack. So gone are all the multi-conductor cables we talked about, gone are the excessive cable trays, gone is the need for conduit, along with labeling of individual wires, the potential for errors and the maintenance headaches. We now have all of our I/O devices, safe and standard, sitting on a single cable, and communication to the PLC is also on that single cable. So everything's on one 2-wire cable. So further, mapping into the PLC is simplified. The OSI master presents the network's data as simple I/O into the PLC data tables. The result is that diagnostics and monitoring are accomplished pretty easily. Which e-stop is activated, the status of the interlocks, the status of the contactors, all that's handled over the single OSI network cable, enabling much smoother assembly, obviously, commissioning, startup, and maintenance like we talked about. In addition, the outputs can now be controlled independently. Remember I said that the hardwired network topology really lends itself to a very stiff and unflexible application. Now contactor 1 here doesn't necessarily have to be turned off when contactor number 2 does. So that allows for a lot more flexibility in the control scheme. This allows us to do zone control, for instance, and that's real easy to accomplish using the OSIsafe technology. So how does the OSIsafe work? How does this scheme work? Well, the OSIsafe functions are parameterized in the safety monitor, and the way that's done is using a software called Osimon. And in this software, you simply drag components and functions from the library you see there on the left into the window on the right, connect them together in the control scheme you want, and then download that to the safety monitor. That's it. Then away you go. It's really, really simple, and it's as easy as it looks here. The safety monitor then listens on the network to the safety devices, and it makes decisions based on what it hears and then reacts according to this parameterization that's been downloaded into it. So here's how that safe communication works. I said there was a special method of communication. Every OSIsafe slave that's manufactured provides a unique 32-bit code sequence. So since there are over 4 billion possibilities, there's no two devices that are going to have the same code ever. And the OSI master polls all slaves on the network, including safe slaves, just as it does the standard slaves. And the safety slave responds a little differently than the standard slave does. It responds with this unique 32-bit code sequence. And that code sequence changes if the safety slave is activated, or if there's a fault, or obviously if there's a communication problem, then that code wouldn't get back to the safety monitor. So the safety monitor, as I said a moment ago, has been parameterized using this Osimon software, and during network commissioning, the safety monitor has learned all of the code sequences for each of the connected safety slaves. So once it's in operation, the safety monitor constantly is comparing the received codes from each device against the expected codes. If at any time a received code sequence is not what's expected by the safety monitor, a decision is made in the safety monitor as per its parameterization, and the safety monitor forwards its decision to the safe output device. In this case, the top 4-bit sequence in the received code table is different from what was expected. So the safety monitor is going to tell the safe output device to shut down the contactors, because that's how we parameterized it. The safe output device, having received the command to shut down its outputs, again, because it's a unique 32-bit code sequence, we know that it's that output device that's going to react. It switches the contactors off and effects a safe shutdown of the machine. Now that's greatly simplified, but to summarize, all safe slaves operate via a 32-bit code sequence. Safe inputs can detect an unsafe condition and change their 32-bit response, which is monitored by the safety monitor. The safety monitor compares expected versus received values, and if there's a delta, it forwards a control decision based on what you've programmed it to do, and the output device then safely shuts down the appropriate circuit. So again, key is that the transmitted 32-bit code sequence must match what's in the safety monitor, otherwise the safety monitor prompts a shutdown or it reacts in the way that you've programmed it. So if there's any fault in a device, or an activation of a device, or loss of communication with the device, the safety monitor is going to prompt that safe shutdown. Okay, I hope that was informative. Please, again, if you have any questions, feel free to ask via the question and answer function in the webinar interface, and we'll do our best to answer right after the presentation. And now I'd like to turn it over to Kartik Vashi, who will show some real-world applications and solutions using OSIsafe technology. Kartik? Kartik appears to be muted.
Thank you, Glenn. Thank you for providing our audience information on the basics of safety and the basics on ASI safety, which is what we call SAW, safety at work. Now I would like to talk about the real life applications and solutions. So if we look at this next slide, here we have a machine, and this machine has many guard locking interlocks and light curtains on this machine. In this process of locking and unlocking the guard door interlock, it requires to have a request to enter controls. So because it's a locking switch, you need a request to enter, as well as it requires a control to lock once the operator has exited the machine. Also, the machine has a reset button to reset the safety function. And once the reset of the safety function is done, you need a lock command. So since this machine has a reset command, a lock command, and an unlock command for each interlock, additionally, we have also emergency stop for each interlocking door entry areas. So here we have 16 door locking interlocking switches, and we have 16 emergency stops, and we have 48 push buttons. And why 48 push buttons? Because we have lock, unlock, and a reset function at each locking door interlock. And then additionally, in the frequently accessed areas where you see the small gaps in the machine, from the side view, that's where we have the light curtains. So if you look at this machine, I mean, if you look wiring all these 48 push buttons and 16 stops and 16 door interlocks with lock unlock functions, we have a lot of functions in this machinery. Then we look at a smaller size machine where this is a machine where we have an entry-exit area where the box is entering and exiting for taping of that box. So it's a taping machine where we are using two light curtains. One is an entry area to the machine and one is an exit area to the machine for the box to enter. So we are using a muting function in this light curtain. Additionally, it has also door interlocks. So because the machine, the side of the machine has the easily accessible doors to the taping machine, you have 4 door interlocks with locking functions. So again, we need lock, unlock, and a reset function with an emergency stop. So having even a small machine like this, we have 2 light curtains and 4 door interlocks with an emergency stop with lock, unlock, and a reset function. So even a small machine like this has a small amount of complexity. Obviously, the big machine that we saw first, it definitely has the complexity, but this is a smaller size machine, but it also has complexity due to muting. So when we talk about solutions for these 2 applications that we saw, where the large machine has 16 door interlock switches and you have multiple control stations, and if we take the control station as an example, we have 12 multi-conductors, conductor cable that we would need for a 3 push button station. Additionally, if we add e-stop to it, now we are looking at 16 multi-conductor cable that you would have to take back into a junction box or take back into your main panel where you would have to wire all this. But when we talk about AS interface, safety at work solution is chosen, the button station have simple 4-wire quick connect, and that's a huge advantage, having a quick connect solution with the which directly goes on to the yellow cable for Aussie. This makes the installation and the cabling and the wiring cost much more simpler and cost effective. Then we add, if we take a step forward, we have, in the example that we saw, we had 16 door interlocks, and if you imagine, as soon as we add the locking interlock, now we are looking, with the combination of the control station, we are looking at 24 conductors that you would have to wire back into your main panel. So you first need a large size multi-conductor cable, and that has to run back into the panel. The cost is enormous. In that case, when ASI Safe is used, obviously the implementation becomes much easier, because now you have a quick connect solution with 4-conductor cable that goes onto the ASI flat cable. So it becomes a very simple solution when we have a complexity in the examples that we saw. Here is another real-life example that I would like to show you. The conventional way of wiring interlocking switch or an emergency stop. Here we have a dual-channel circuit where we have the input channels where it says door, which is connected to terminal S11, S12, S21, 22, and the contactors are connected with 13, 14, 23, 24, and then you have a feedback circuit for those contactors for any failure detection with a reset button. So when we look at this type of circuit is designed to monitor or detect any accumulation of fault, or a fault such as cross short or short circuit into the input device or the output device. But the real problem occurs in real life when we daisy chain these type of interlocking devices, and when the circuits are designed, but the design is done with series connection to save the wiring cost, or require less safety relays, or require less safety inputs to the safety PLC, the safety designers and machine designers may forget to take fault accumulation into consideration. And what we have, you know, sometimes you think that we are achieving the highest you can achieve when you are series connecting these type of door interlocks or emergency stop. The highest level of safety that you can have is a category 3 performance level D. But there is more to this than you think, as this issue has been recognized as a critical issue when the door switches are series connected. And door switches, especially when their door switches are series connected, but at the same time they're frequently used. When they're frequently used, you may think that you're getting category 3 performance level D, but you may not, where the guidance, this guidance actually comes from ISO 14119 standard, which is the standard that discusses interlocking devices and the design aspects of interlocking devices. In the technical report, it actually gives us even further detail when we have more than 4 switches series connected, and if one of the switch being frequently used, you may not actually get a performance level D category 3. So when we look at the actual table from the standard, it's actually showing us when you have more than one switch, or from the 5 switches series connected, you have one switch which is being used frequently, less than once per hour, you may have a performance level that would be a performance level C category 2 or category 1 based on the application. So sometimes you may think that what you are getting with the conventional way of wiring interlocking devices, you may not be getting that. But with ASI, or the ASI interface with safety, it becomes a very simple solution, because everything that you do, or all the installation that you do, does not require complex engineering practices, and by default the way Glenn explained it to you, it is a category 4 performance level E solution. So anything, all the interlock devices or the emergency stop, all the safety devices that you wire into the yellow cable, it's by default a performance level E category 4 safety solution. So when we talk about solutions, that we have various ways of completing the entire safety circuit with the higher level PLC that includes status of all these ASI slave devices back into the main PLC. In this example, we have integrated ASI solution. The main PLC has the ASI master with safety monitor, which monitors the safety slaves in the field connected on the ASI network. Also, the same network allows the field safety output cards to trigger the motor contactors. Integrated I/O mapping to the main PLC allows diagnostics information to float to the HMI for the status for each slave devices. If we talk about another solution in the same line, we have safety separated with possible with ASI master monitor is built in with monitoring and has a built-in gateway that can communicate to the higher level PLC to transfer information for each slave devices back into the higher level PLC, so you can see the diagnostics onto the HMI. Also, the second solution is an integrated solution with the Profi Safe solution, where we have an ASI safety master gateway, which allows us the communication directly back into the main PLC with the safe communication. So now your outputs can be controlled by the main processor instead of the I/O, which is in the field. But you can certainly add I/Os, meaning output cards, to the field, as I showed you in the earlier example. Then the same idea applies here for ProfiNet solution. So based on the type of communication that you may have available with the higher level PLC at a customer site, you can integrate that very easily because there's many solutions that we have for the gateway systems, or the ASI master monitor with the gateway built in. So here, once again, we have a ProfiNet with non-safe communication to the higher level PLC for diagnostics, as well as we have ProfiSafe communication to the higher level PLC for a safe communication. Same thing applies with the Ethernet IP. We have the solution with Ethernet IP for non-safe communication back into the higher level PLC for each ASI slave status. At the same time, we have a Ethernet IP SIP safety available that you can transfer all this information back into the higher level PLC, so you can control your safety outputs in the higher level, from the higher level PLC, or the safety drive system that you may have connected with the safe PLC. So there's many ways of providing a complete solution for the AS interface. Of course, the idea of ASI stops at the yellow cable, but also you have a gateway communication that talks to the higher level PLC as well. And some of the PLC system, as I showed you in the first example, has built-in communication and it can work as an AS interface master monitor module as well. So when we look at cost perspective, the ASI, the engineering and time sums up to all with the cost. And when a small system requirements are there, and the length of the cable from the sensor to the enclosure is 4 meters or so, it is still advisable to use ASI as there is at least 8% saving compared to the conventional way of doing things. Conventionally, 62% of the cost is for the components, and the installation in the field is 19%, and we have 19% cost involvement in the enclosure. So whatever the the terminal blocks or the name tags and etc., all that cost is added with 19%. Whereas when we compare it with AS interface, we have 85% component cost. Yes, the component cost is higher due to integrated ASI chip. We have 5% for the installation in the field because of the yellow cable and passive connector possibility. We don't need junction box and accessories in the field. And we have only 2% cost to the enclosure installation. So enclosure space is drastically reduced due to less wiring because all the wiring is done in the field on the yellow ASI cable. When we look at the larger size machine, which we saw in an example, there's definitely more advantage from the cost perspective. There's 32% cost advantage compared to the conventional way of doing things. Conventionally, there's 50% for the parts, 25% for the installation in the field, and 25% for the enclosure installation. On the other hand, with ASI, 55% of the cost comes from the parts, but only 7% for the field installation and 4% only for the enclosure installation. So huge cost advantages we have, and this is the analysis that we have done. And again, I'm briefly describing it based on the applications we saw in the beginning. So if I was to summarize what we talked about, the advantages of ASI safety at work, here we are showing the summary. Of course, the easy wiring, maintenance, and diagnostics. It's still just a 2-wire cable, and you simply attach devices onto the cable. Either standard or either standard or safety devices on the same cable. The safety logic is simple, programmable drag and drop logic, as you have seen in the earlier slide. Is safety at work also? It's a performance level E category 4 SIL3 solution, and it's expandable up to 31 safety nodes in a network. So we have huge advantages to this solution. So mainly targeting the machine builders, the complexity in the machine design is reduced. As Glenn talked about, the process of designing and redesigning the machine until the risk has been reduced, AS safety lends itself to a simpler design because of the simplistic nature of the technology. This leads to reduces engineering complexity and the reduction in labor cost. It reduced commissioning time due to increased diagnostics, and this all leads to reduced overall cost and faster time to the market for the machine builder. So the machine can go out faster into the market, and due to this, the savings in engineering cost and the design cost. Also, the end users also has huge advantages, and the machine has higher availability due to simplified diagnostics and maintenance. Fault sources are reduced since wiring is very simple. As Glenn described to you earlier, the wiring faults can occur, and you have a very hard time diagnosing that fault. Here, the diagnosing of fault is very simple. At the same time, hot swap to the slave means the machine doesn't necessarily have to be out of commission for repair, because it's very simple to replace an ASI device compared to the conventional devices. When the time comes to expand or modify the machine, which in the end user environment that's quite frequently done, safety is simple to expand and configure as well. All this means in the end, user can produce a high efficiency leading to increased revenue and increased profit margins. So obviously for an end user also, this is a huge advantage. Additionally, I would like to give you some information on the workshops we do. We have done 2 so far throughout US and Canada this year. We have 1 more coming up, and during that workshop, we set up a live network, and it's not us setting that up, it's actually the attendees setting that up. So it's a real hands-on workshop that we do. We also do the PLC integration, just like what I showed you in a solution slide. We communicate a Aussie master monitor with a Siemens PLC. Also, we do communication to the higher level PLC with Rockwell PLC with the Aussie master monitor. At the same time, we talk about analog data, safety at work, as well as diagnostics information, how to diagnose a problem into the Aussie network. So we talk about all that. It's hands-on. It's highly recommended for controls engineers, for maintenance managers, for design engineers, for director of engineering, people like those. It's really highly recommended workshop that you would want to attend. So the one that is coming up is in Ohio, Cincinnati, and it's on October 24th. So please visit the website to register yourself. The Aussie organization website has the registration. Follow us on LinkedIn, so we constantly update the registration forms via LinkedIn. So you can various ways you can register for the workshops or any other activities that we do as part of the Aussie organization. Next thing we have is I'm gonna transfer it over for question and answers. So John, I would like to take over for. I would like you to take over from here.
All right. Well, thank you, Kartik and Glenn. We'll now move into the Q&A portion of the presentation. If you have a question for our speakers, please submit it now by typing in the Q&A panel and click Submit. If we do not have an opportunity to address your questions, we'll answer them by email. So we have a few questions here. Helga, perhaps you'd like to take this one? It looks like a 2-part question. I understand that it is possible to connect AS interface safety devices to the network. Could you please explain how and if I can use conventional dry contact or electronic output safety devices? And part 2 is, how are those connected and integrated?
Okay, so most everything the 2 gentlemen talked about was on a conceptual level, assuming that the AS interface safety, I don't want to say safety chip, but the safety portion was integrated into the device. If you want to use a conventional safety e-stop, let's say, that has dry contacts, what you would do is you would purchase from any of the many manufacturers, you would purchase a safety coupling module. It's essentially a standard. It looks like a standard Aussie module, but has the safety circuit in there so that it has a safe input. And then the 2 dry contacts from the device, from your safety device, are simply connected to those inputs, and that together serves exactly the same purpose. So from that point on, once that connection has been made, 4 leads going from the safety device to this I/O block, this safe rated I/O block, it is exactly the same as what was shown throughout the the presentations. So there really is no difference in integration. It's just that initial step of running the 4 contacts. And the same is true for devices with electronic OSSDs. Now, there are 2 different kinds of safety coupling modules, the ones designed for electronic contacts and the ones designed for mechanical contacts. So use the appropriate one for the type of safety device that's going to be used.
All right, well, thank you, Helga, for that answer. I have another question here. How do I know what safety level I need to be at? Or should I just go to the highest level? Glenn, would you like to address that?
Yeah, thanks, John. I think all of us on the panel here have run into machine builders that simply assume they should just go to the highest safety level, but I think that can add considerable and really unnecessary cost and effort. So the proper way, as I said, to determine what level you need to be at is through a formal risk assessment. There are companies out there who do that as for a living. They provide that service, and they would evaluate the machine's hazards and those associated risks, and then provide a report that details the required safety level and the reasons why. And most times those services include recommendations that the machine builder should take in order to meet those required safety levels.
All right, thank you, Glenn. Another question. What is the typical update rate, speed of a small to medium-sized OSI network in terms of update rate of safety standard inputs? Would someone like to address that?
I can take that. So this is a really, really good question because it somehow hits on the important part. AS interface safety at work is, in a sense, a layer on top of ASI. If you remember back in Glenn's presentation, he showed these safety codes that had to be transmitted. So the mechanism to transfer data is ASI, and really the safety message is encapsulated in these 8 packets of 4 bits, which equates to 32 bits. So having said that, let me get to the numbers. A AS interface network updates at roughly 160 microseconds per module on the network, meaning if you have 10 modules, it updates about in 10 milliseconds. If you have 10 modules, 1.5 milliseconds. If you have 20 modules, that would be then about, let's call it 3 milliseconds. Now, in order for a safety device to communicate to the safety monitor the state released, which is essentially the machine is running, the full safety code sequence will have to be transmitted. That means that the network has to go through 8 cycles of updating before a safety contact goes from an open state to a closed state, essentially turning on the machine. So if you have, again, a small system with 10 devices, updating in 1.5 milliseconds times 8, what is that? That's 12 milliseconds. So releasing an e-stop and then hitting the reset button takes about 12 milliseconds for all the data to be where it needs to be so that it can turn on. Now then there's a little bit of processor overhead and there's a little bit of a relay time. Switching off is very different. Switching off is instantaneous. Glenn had a very nice graphic also where he showed the comparison between these tables, and as soon as the first discrepancy shows up, the shutdown sequence is initiated. So there you can argue a small system that updates in 1.5 milliseconds will communicate the fact shut down in 1.5 milliseconds, and from there on out it's simply a little bit of processor time and a little bit of time that the actual relays need in order to open up.
All right, thank you, Helga. Another question, what is considered a module in the description of update rate?
Well, that is sort of a follow-up to mine, so if you guys don't mind, I'll take that. A module really is a block, an I/O block. So that's another word for I/O block. A module also is an entity that has one address. So it's an I/O block that has exactly one ASI chip in it. It has one address assigned to it. So module, I/O block go interchangeably.
All right, thank you. I think we have time for one more question. Kartik, this looks like something you might be able to answer. Can I create different zones even though all the safety components are connected on the same yellow cable? For example, if I have an e-stop function to stop the entire machine and a light curtain, which is another function, or a gate switch, which could be another function, as compared to the light curtain or the e-stop?
Thanks, John. It's a good question. Yes, that's the whole idea, is to be able to create this logic in the Azimon software and actuate different outputs based on the safety function required to actuate the specific output. Since each devices are addressed at the beginning of this setup procedure, they can be called in for logic based on the requirement of that safety function. So yes, that's the whole idea, that they are different. Each safety slaves are addressed differently, and they're programmed in the Azimon to actuate different outputs. So certainly different zones can be created by the software.
All right, thank you, Kartik. I think that's about it. I'd like to thank Kartik, Glenn, and Helga for providing us with so much information, and thank you to our audience for your questions and attending today's event. This presentation will be available shortly in an on-demand format. As a registered user, you will receive an email with detailed information on how to access the replay. Please feel free to invite your colleagues and peers who were not able to attend the event. The presentation materials are owned and copyrighted by AS Interface, and the individual speakers are solely responsible for their content and opinions. Thanks for joining us, and have a great rest of your day.